how blood pressure is measured. And we typically use a blood pressure cuff. And what we do is we compress the artery. So it's typically taken around the brachial artery, usually in the left side, it's closer to the heart. And we put that blood pressure cuff on, we squeeze or obstruct the flow of blood in the brachial artery, and we listen to the turbulence of blood flow in the artery. Now, typically, we need a higher pressure than what's in the vessel in order to compress the vessel, right? Does that make sense? So that's sort of the first part. In order to compress the brachial artery, I'm going to need to apply more pressure than the pressure of the blood that's flowing in that brachial artery. And this is how we find out what the highest pressure is. This is how we find the systolic pressure. Let's actually jump to this slide where we can illustrate this. Okay, so let's illustrate this here on this slide, and then I'll jump back. So we typically put on the cuff, right? And the cuff is squeezing the arm so tightly that it is obstructing the brachial artery on the flow. And so when we no longer hear blood flow, we know that at that pressure, we have exceeded the pressure that is in the brachial artery. And that is how we document our systolic pressure. Now, what we do at this point is slowly release the cuff. So we're going to slowly release the pressure in the cuff, and we're going to hear some turbulence. These are called corticoff sounds. And basically, when blood is flowing through a narrowed artery, it's turbulent. And as we listen to that turbulence, we're going to try to indicate or find when the turbulence stops. And at that point, we know that the vessel has completely opened up. So let's jump back one more time. We squeeze the vessel all the way closed. Okay, we no longer hear blood flowing. We slowly release it. And at this point, we can hear some turbulence. When the turbulence stops, we know that the vessel has fully opened up. And this is where we document our lowest pressure. This is our diastolic pressure. Okay. So when the corticoff sounds disappear, this is where the lowest pressure is, and this is how we get our diastolic pressure. So blood that's flowing smoothly through the vessel, it makes no sound. Blood that's flowing turbulently through the vessel, or that's flowing through a narrowed vessel, it's going to make some sound or some turbulence. And so when that turbulence disappears, we know the vessel has fully opened up, it's fully patent, and at that point, this is our lowest pressure. I hope that makes sense. So we've identified our highest pressure, the amount of pressure that it takes to occlude this vessel. That's systolic. We've also identified our lowest pressure, the lowest amount of pressure in that vessel, because at this point, the flow of blood in the vessel has overcome the pressure that we are applying to the vessel. And so what we have here is systolic and diastolic pressure. And let's go back here. Oops. Okay. So this is basically the same. So let's jump back here. So that gives us a reading of our blood pressure. That's systolic pressure over diastolic pressure. And that is typically 110 millimeters of mercury divided by 70, right? 110 over 70. So our highest pressure is usually about 110, and our lowest pressure is usually about 70. Now, other important interpretations of our blood pressure is the pulse pressure, okay? The pulse pressure is our systolic pressure minus our diastolic pressure, and that's usually about 40 millimeters of mercury. Now, the pulse pressure tells us how rigid the vessel is. It's a really important indicator of the elasticity of the vessel. Does anyone know why? Why would the pulse pressure be an indicator of the elasticity of the vessel? Right, good. So it shows how well or how long it takes for that artery to recoil on itself. Think about it. If the diastolic pressure were, say, 10, we would have a bigger pulse pressure, right? We'd have 110 minus 10. This would give us a big pulse pressure of about 100. And that would tell us that the vessel did not recoil. right? It did not recoil because we got our pressure way too low when it should have been up at about 70. So remember, during diastole, which is where we document this second pressure, that diastolic pressure, there needs to be maintenance of that perfusion. And as we mentioned before, having an artery that recoils very nicely is what keeps our diastolic pressure up. If the artery is not recoiling, the diastolic pressure is going to be really low, and we're going to have a really large pulse pressure. We usually see this in older individuals that have thickened, hardened arteries. They usually have really large pulse pressures, and that dictates to us how much elasticity that artery has. Another important interpretation is mean arterial pressure. This is a value that we've seen before differently, but this is actually how we can calculate that value, right? What did we associate mean arterial pressure with? What did we associate mean arterial pressure with? In that last packet, what did we talk about mean arterial pressure as being? Excellent. The driving force for our circulation. Perfect. So the mean arterial pressure is telling us how well we have flow, right? How well we have vascularization or perfusion. And in the formula to calculate mean arterial pressure, we take the systolic pressure and we add it to the diastolic pressure times 2 divided by 3, okay? Why would we multiply the diastolic pressure by 2? Why would we multiply the diastolic pressure by 2? If this is an average indication, or this is an indication of the average pressure throughout the entire cardiac cycle, why would we multiply the diastolic pressure by 2? This goes back to last semester, something about diastole. So we know the heart spends much more time in diastole, right? Round about twice as much, twice as long in diastole. So if we're looking at the average pressure across the entire cardiac cycle, we're going to need to take diastolic pressure into account twice. The heart spends much more time in diastole than it does in systole. And so looking at the mean arterial pressure, we're going to look at systolic pressure 2 times the diastolic pressure divided by 3, okay? And an example of what that looks like is about 83.3 millimeters of mercury. Okay, so these are some important pressures and some important interpretations of our blood pressure that we can use to tell us about the state of our arteries.